So here we're going to look at Pauling's rule number 2, and this is related to this idea of the electrostatic valence principle or electrostatic valence bond strength. Now before we introduce that, we're going to review just briefly the idea of coordination number. So there's another video where we talk about how the coordination number is related to radius ratios, and you can refer to that other video on Pauling's rule number 1. The way it relates here is that the coordination number tells us about the number of bonds that a given cation will form with anions. So let's say we have a cation of silicon, and that silicon atom is bonded to, let's say, 4 oxygen atoms. Then we would say that the coordination number for silicon is 4. Let's go ahead and erase the chalkboard and look at the implications for that. So for silicon in 4-fold coordination, let's say we have the mineral quartz, so it's bonded to 2 oxygens per formula unit. Then that silicon atom with a 4+ charge is going to be dividing that 4+ charge amongst 4 separate bonds. So this is where we get the electrostatic valence bond strength, or we'll abbreviate that EVBS. So 4+ divided by 4 gives us 1, a positive 1 charge that silica in 4-fold coordination can donate to each of the oxygen bonds. So again, let's consider silicon, and let's say it is bonded to 4 oxygens, so 1, 2, 3, and 4. Then each of those bonds will have a +1 charge based on this idea of electrostatic valence bond strength. Now, to give a counterexample, let's take a look at silicon in 6-fold coordination. So we would still have a 4+ charge, but now that 4+ charge is being distributed between 6 bonds. So if silicon is in 6-fold coordination, there's only a +2/3 charge that can be devoted to each bond. So with silicon bonded to, let's say, 6 oxygens, 1, 2, 3, 4, 5, 6. So here are 6 oxygens here. Each of those bonds is only going to have a magnitude of +2/3. So 2/3 there, 2/3 there, and so on for all of these bonds. That bond here will be weaker than this case here, where we have a 1+ bond, a 1+ charge being donated to each bond with oxygen for the 4+ case. So that's where the electrostatic bond strength comes in. The bond strength is directly proportional to this value here that we get by taking the charge and dividing it by the coordination number. So now let's take a closer look at the second rule as it is normally stated. And for the second rule, we're going to take silicon in this case of quartz, and we're going to first have to determine this value n, the coordination number. So with the second rule, it's usually stated with respect to what kind of charges are reaching the anion. So let's take a look at how we might figure out the coordination number n for oxygen. We don't necessarily need to rely on radius ratios. If we know that silicon is in 4-fold coordination, since we only have 1 anion on this side, we can write a very simple equation where we take the coordination number 4 and then multiply it by the number of atoms that pertain to that coordination number. There's just 1 silicon atom, and so we would take 4 and multiply it by 1. And then on the anion side of this, we would have the coordination number n, which we want to find out, and multiply it by the number of atoms too. So this is 4. 4 times 1 is 4, and that is equal to 2n. And so n is equal to 2. So we can erase this fellow here and say that oxygen is going to be in 2-fold coordination. So for the case of quartz, where silicon is in 4-fold coordination and we have a formula of SiO2, if that silicon is bonded to 4 oxygens, then those 4 oxygens must in turn be only bonded to 2 silicon atoms. So what does that mean for the amount of charge that's being donated to each silicon atom? Let's rewrite the formula here. We've got SiO2. Oxygen is in 2-fold coordination, as we've just determined, and silicon in 4-fold coordination. So for our oxygen atom, let's draw this oxygen atom here, and it has 2 bonds emanating from it. One over here, connected to a silicon atom, and another over here, connected to another silicon atom. As we determined earlier, for silicon in 4-fold coordination, its electrostatic valence bond strength is a +1, so that silicon atom here only has a 1+ charge that it can donate to that oxygen atom over here. And likewise, this silicon atom here has a 1+ charge that it will donate. But the good news for oxygen is this. Take a look at this balance. Oxygen has a 2- charge, and the total positive charge that's reaching oxygen is also +2. So we've got a +2 charge emanating from the 2 silicon bonds that are reaching oxygen, and that matches or cancels the 2- charge on oxygen itself. So that means in Pauling's rules that we would say that this is the most stable arrangement. The case where silicon is in 4-fold and oxygen is in 2-fold, and where these bonds match the charge on the anion, that is the most stable case. That's the essence of Pauling's second rule. And so what we've discovered here is that quartz is stable. Okay, no surprise. But if you had a different kind of compound where you weren't sure of the atomic arrangements, then you can use radius ratios to guess at some coordination numbers for the cation, and then you could play the similar kind of mathematical game to determine possible coordination numbers for the anion, and then see if the charges match up in that structure. If they did not, then the structure would not be stable. But if they come close to being able to match, I think in Pauling's original textbook, he showed that plus or minus 1/6 of a charge is considered a pretty good match and within the error, at least at that time. Then you have something that is relatively stable and so would represent a possible structure.